Is electrical resistance caused by electrons colliding with atoms when current flows? Is it caused by electrons colliding with each other? Resistance in electricity occurs when electrons collide with atoms as they flow through a conductor. Current is driven by the movement of free electrons within the wire, and these free electrons lose energy when they collide with the atoms in the wire. This energy is converted into heat, causing the wire to heat up. The resistance due to electron-electron collisions is minimal because electrons are tiny particles with a low probability of colliding with each other. Furthermore, since electrons move in opposite directions, the likelihood of energy loss from collisions is reduced. Hence, electrical resistance is primarily attributed to electrons colliding with atoms within the conductor. However, at high temperatures, resistance due to electron-electron collisions may increase as the electrons gain more kinetic energy, leading to a higher collision probability. Additionally, the presence of impurities in the wire can increase resistance, as impurities can impose an electric field on electrons, hindering their motion. So, in the case of high temperatures, does electrical resistance also increase as the movement of atoms increases? In the case of high temperatures, the movement of atoms increases, resulting in an increase in electrical resistance. This is because the elevated motion of atoms leads to a higher frequency of collisions between atoms and electrons. When atoms are in motion, electrons have a higher probability of colliding with them. During these collisions, electrons lose energy, which is then converted into heat, causing the wire to heat up. Consequently, at high temperatures, electrical resistance increases, making it more difficult for current to flow. Indeed, the phenomenon of increased electrical resistance at high temperatures is observed in various fields. For instance, electric thermometers utilize the property of electrical resistance changing with temperature to measure temperature. Additionally, electrical insulators, which are materials with very high electrical resistance, can experience a decrease in insulation effectiveness when used at high temperatures due to the increase in electrical resistance. Therefore, when designing electrical circuits for high temperature environments, it's essential to consider the increase in electrical resistance and choose appropriate components accordingly. Then, when the temperature drops to near absolute temperature, can the movement of atoms decrease in a certain temperature range and the electrical resistance approach zero? As temperature approaches absolute zero, a phenomenon known as superconductivity can occur, where the movement of atoms decreases, and electrical resistance approaches zero. At lower temperatures, the slower motion of atoms results in a reduction in the frequency of collisions between atoms and electrons. As a consequence, the probability of electrons losing energy through collisions with atoms decreases. Therefore, electrical resistance decreases, making it easier for electric current to flow. In the state of superconductivity, electrical resistance becomes virtually zero, allowing electric current to flow without any resistance. Superconductivity was first discovered by Heike Kamerlingh-Onnes in 1911 when he observed that the electrical resistance of mercury disappeared at temperatures near 0 Kelvin, minus 273.15 degrees Celsius. Since then, superconductivity has been found in various materials, and to date, around 200 different superconducting materials are known. Superconductors, due to their zero electrical resistance, exhibit minimal energy loss. Utilizing superconductors can significantly reduce power losses and enhance electrical efficiency. Moreover, superconductors are capable of generating strong magnetic fields, making them applicable in various fields such as nuclear fusion, maglev trains, and medical applications like magnetic resonance imaging, MRI. Hence, as temperature approaches absolute zero, the reduction in atomic motion leads to a phenomenon where electrical resistance approaches zero, known as superconductivity. Can superconductivity occur in most metals, such as iron, when the temperature is lowered? As temperature decreases, most metals do not exhibit the phenomenon of superconductivity. In fact, for most metals, as temperature decreases, electrical resistance decreases, but it does not reach zero, even as it approaches absolute zero. Superconductivity requires the alignment of electron spins. Metals have random electron spin orientations, making the occurrence of superconductivity challenging. However, some metals, such as iron, can experience a phenomenon where electron spins become aligned as temperature decreases, providing a potential for superconductivity. In reality, in 2008, a group of Japanese researchers discovered superconductivity in iron arsenic compounds. These compounds were found to exhibit zero electrical resistance at temperatures below -260 degrees Celsius. Subsequently, various superconducting materials based on iron were developed. The critical temperature, the temperature at which superconductivity occurs, for iron-based superconductors has reached as high as -231 degrees Celsius. Therefore, as temperature decreases, superconductivity can occur in certain metals like iron. However, these metals have extremely low critical temperatures, making commercialization challenging. To enable the practical use of superconductivity, it is necessary to raise the critical temperature. Research is actively underway to achieve this by developing new superconducting materials based on iron or by improving the structures of existing materials.